in some cases, we may have a function that lies above the x-axis in part of the integral and below the x-axis in part of the integral. So let's look at an example like that. Suppose I have the function f of x is equal to x cubed minus 6x on the interval from 0 to 3. Now we've already looked at this example, okay, and we actually calculated the integral using the limit of the Riemann sum. We're going to now redo it using the fundamental theorem of calculus. So I want to know the integral from 0 to 3 of x cubed minus 6x dx. Instead of using the limit of the Riemann sum, which is a long process, we're just going to use the fundamental theorem of calculus. So this is our function, and we need the antiderivative, which is x to the fourth over 4 minus 6x squared over 2. And then we need to evaluate it between 0 and 3. Okay? So just to simplify it, 6 divided by 2 is 3. So I'll just rewrite this as a 3. Now we're going to plug in the upper limit first. So it's going to be 3 to the fourth over 4 minus, and when I plug in a 3 here, it's going to be 3 squared times 3. So I'll actually write it out in 2 steps. So it's going to be 3 times 3 squared. That's from the upper limit. And then minus, when we plug in the lower limit, we're just going to get a 0 minus 0. So that just works out to be 0. When we work this out, 3 to the fourth is 81. So 81 over 4. And then 3 times 3 squared is going to be minus 27. Okay? If we wanted to simplify this, we should make a common denominator. So the common denominator would be 4 over 4. Okay, so if I multiply this by 4 now, so 27 times 4 is going to be 108. So 7 times 4 is 28. So minus 108 over 4. Now when you subtract this, we're going to get minus 27 over 4. Notice that the answer came out to be negative. Okay? I want to show you the graph of what this function looks like so that we can understand why the answer came out to be negative. Okay, so x cubed minus 6x on the interval from 0 to 3. We should be able to easily graph this function, and it's actually good practice because in chapter 4, we learned how to graph functions, right? We can find the critical points, we can find the maximums, the minimums, and all of that, especially since it's on a closed interval. Okay, so I'm just going to show you the graph, and the easiest way to find the graph, I think, is to realize that it's a polynomial. If I factor out the x, I get this. So I'm just completely factoring. And the reason I'm factoring is that this is going to tell me the zeros of the function. So if I set this equal to 0, there are 3 zeros. And remember, the zeros are where the function crossed the x-axis. Like this. So this function is just cubic, so it looks like this. I actually don't even need the derivatives. I don't need the first derivative or the second derivative in this problem, although you could use it. Okay, the function looks like this. Now, I'm only interested in the region from 0 to 3. Okay, so now I'm going to redraw it. I'm going to erase the part that I don't want. I only want the region between 0 and 3. So I don't want this part. Here's where x is 0. And the square root of 6 is a little bit less than 3, so I'm just going to put the 3 here. Okay, so that's the region that I want. Now, when I evaluate the integral from 0 to 3 of this function, remember that when the function is positive, this will give me the area under the curve, but where the function is negative, it will give me the negative of the area. So look at this function. In certain regions, the function is above the x-axis. So from square root of 6 to 3, the function is above the x-axis. So when I integrate, this part is going to come out to be a positive number. But this part of the curve is below the x-axis. So when I integrate, this part will come out to be negative. Okay? And since this region is bigger than this region, this negative part is going to kind of dominate. So if I took this amount, which was negative, and this amount, which is positive, and add them together, the answer should come out to be negative, right? If I take a negative number that is bigger in absolute value than this positive region, and I add it together, I'm still going to get a negative result. Okay? So the point with this example that I wanted to show is that when you evaluate an integral, okay, if the function is completely above the x-axis, the answer will be positive. If the function is completely below the x-axis, the answer will be negative. And if the function is partially above and partially below, it depends upon the size of the region. If the region below the x-axis is bigger than the region above the x-axis, the answer will come out to be negative. And if the region above the x-axis is bigger than below, the answer will come out to be positive. In fact, there's a property that says you can split your integral up into pieces. So instead of integrating from 0 to 3, you could split it up and integrate instead from 0 to square root of 6, and then the rest of the way. So the rest of the way would be the square root of 6 to 3. So for instance, if I wanted to, instead of integrating directly from 0 to 3, all the way across, I could integrate from 0 to the square root of 6, and then from the square root of 6 to 3. Okay? Or you could split up the interval anywhere you want. So if instead of integrating from 0 to 3, you could integrate from 0 to 1 plus 1 to 3. So that's a theorem that says that you can split up the interval. You'll get the same answer either way. Okay? Now in this part where I split it up from the integral from 0 to the square root of 6, that's this green region. I know that this green region lies below the x-axis, so this is going to come out to be negative. So this part of the integral will come out to be negative. You can calculate it and see what you get. This part of the interval from the square root of 6 to 3 is the red part. It's above the x-axis, so that part will come out to be positive. But because the region below the x-axis is bigger than the region above the x-axis, the answer is going to be negative at the end.